Now let's discuss about the equivalent circuit of a UJT. We have seen that a UJT is a N-type bar with two terminals that are represented by the base B1 and B2 and a voltage VBB is applied between the two base terminals with B2 positive with respect to B1. And there is a P region which is called the emitter, which forms PN junction with the N-type bar, and there is a gradient of potential between the two base terminals B1 and B2 in such a way that there is a higher potential at the region base B2 and lower potential is at the region B1. And you can see that more than half of this applied voltage will drop across the region of the emitter and base V1, which is denoted by the voltage V1. So we can say that if we replace this UJT by its equivalent circuit, we can say that there is a resistance across the bar, N-type bar from B2 to B1, of which the resistance between B2 and the emitter junction E is always constant, but the resistance across this emitter and base B1 is varying, which actually depends upon the applied voltage to the emitter junction, that is VE. That we have seen that is when VE is applied, this PN junction may become forward bias. During the forward bias, the resistance of this channel from the section emitter to B1 will be decreased. So we can say that this B2 to E has a particular resistance, and from E emitter to the base B1 will have another resistance, but this resistance is a variable one. So a UJT can be replaced by two resistances in series, with one is a variable resistance, and also in between these two resistances there is a PN junction. A PN junction is otherwise called a diode. So it is replaced by a diode. So if you consider this diagram on the right side, here you can see that there is a resistance RB2 which is connected in series with a variable resistance RB1. In between these two there is a diode D is connected. So this diagram is the equivalent circuit of an unijunction transistor. Here the resistance RB2 actually represents the resistance or the channel resistance of N-type or silicon bar between B2, the base terminal B2, and the emitter junction, that is E. And there is another resistance RB1, which is actually the resistance of the silicon bar between the base B1 and the emitter junction E. This resistance, I told you, is a variable one because its value depends upon the bias voltage across the PN junction, that is the voltage VE. Now the PN junction is represented by the diode D. Now if we consider this equivalent circuit, we can easily explain the action of an UJT. So first of all, consider if there is no voltage applied to the UJT, that is this VE is equal to 0, VBB is equal to 0. No voltage applied voltage applied means VE, VBB are 0. So then the total resistance of this one is given by RBB. So actually RBB represents the resistance of the silicon n-type bar from the base terminals or in between the two base terminals B1 and B2, which is nothing but the sum of the two resistances RB1 and RB2 when there is no voltage. And this value actually lies between, I told you, 5 kilo ohm or 4 kilo ohms to 10 kilo ohms. In practical cases it will vary from 4 to 10 kilo ohms, or usually some others will mention it as from 5 to 10 kilo ohms. Anyway, now if a voltage VBB is applied, between the two base terminals with the emitter open, that is VE is equal to 0, then the voltage will divide across RB2 and RB1. We are interested on the voltage V1. So the voltage V1 is given by when VBB is applied, that is only VBB is applied, the emitter is open, then V1 will be the total current into the resistance R1, that is, since RB1 and RB2 are series, so current will be the same. So I can write it as I into RB1. The current will be the total voltage applied, that is VBB, divided by the total resistance, which is RB1 plus RB2 into RB1. So this is the voltage V1 which appears across the emitter and base terminal V1. So now from this one, if we consider the ratio V1 by VBB, which is equal to RB1 divided by RB1 plus RB2. This ratio is called intrinsic standoff ratio. So intrinsic standoff ratio is the ratio of the voltage which appears across the emitter base terminal B1 and the applied voltage across the two base terminals when emitter is open. It is the ratio of the voltages across the base B1 and emitter terminal and the applied voltage VBB when the emitter terminal is open, and it is usually denoted by the letter eta. So intrinsic standoff ratio eta is given by RB1 divided by RB1 plus RB2, which is actually the voltage V1 divided by the applied voltage VBB. That is, it is the ratio of the voltage which appear across the conducting terminal of the or conducting part of the UJT to the voltage across the or voltage applied across the two base terminals. The value of this eta practically lies in between 0.51 to 82. That means 50 percentage, 51 percentage to 82 percentage of the total applied voltage will drop across the emitter and the base terminal B1. So this voltage across RB1, which is called the V1, represented by V1, is given by eta into VBB. So remember this expression. In terms of the intrinsic standoff ratio, we can express the voltage across the resistance RB1 as eta into VBB, where VBB is the applied voltage across the two base terminals. And this voltage V1, which appearing across this emitter and base terminal B1, reverse biases the diode, therefore the emitter current is 0. So the voltage which is responsible for reverse biasing the PN junction is this voltage V1. Now the third case is we are going to apply the voltage VE, and if we are going to increase it progressively, then the diode will become forward biased when the input voltage exceeds this eta VBB by VD, the forward voltage drop across the silicon diode. That means the PN junction, suppose this is our diode, and we are having a voltage V1 which is applied here, and there is a voltage VD which is the potential barrier, which we know that, which is 0.7 volt for silicon. UJT is consisting of a n-type silicon bar, so it is VD is 0.7. So already here we are applied a positive voltage V1 here because of this VBB. Now if we want to apply a VE up here to make this diode forward biased, the applied voltage which VE, which should be in such a way that whose value should be at least greater than the sum of the V1 and VD. So suppose at a particular voltage VP which appears across the diode, forward biases the diode, then we can call it as the forward voltage drop across the silicon diode. VP will be equal to eta VBB plus VD. So this is the forward voltage drop across the silicon diode. So the applied voltage VE should be greater than this value VP to have the emitter current. So this VP is otherwise called peak point voltage. So VP is equal to eta VBB plus VD. This VD is the forward voltage drop across the silicon diode, and which is 0.7 volt for silicon. So this is the working or the action of an UJT when different voltages are applied. So initially when there is no voltages, there is no current or nothing happens, there is a series resistance RB1 plus RB2 across the bar. Now when the voltage VBB is applied across the two base terminals, it will reverse bias the PN junction, and the voltage which reverse biases the PN junction is given by this expression, that is VB eta into VBB, where eta is the intrinsic standoff ratio. Now we will have to apply a voltage to the emitter circuit in such a way that it should be greater than the peak point voltage, and which is given by eta VBB plus VD, where VD is the forward voltage drop across the silicon diode, which is 0.7 volt, approximately 0.7 volt. So that's all about the action of a unijunction transistor by considering its equivalent circuit. Now let's move on to the characteristics of a UJT. The characteristic of a UJT means it is the curve between the emitter current and the emitter voltage at a particular VBB. Means it is the VE versus IE characteristics at a constant VBB. That means it is a curve between the emitter voltage and the emitter current at a given base voltages, or voltage, a constant voltage between the two base terminals. This is otherwise called emitter characteristics of UJT. Now this figure represents a typical emitter characteristics of an UJT. Here you can see initially in the cutoff region, that means this one represents the cutoff region. As V increases from 0, slight leakage current flows from the terminal V2 to the emitter. That is, when V is switched on and it starts to increase from 0, there will be a leakage current from the across the PN junction, and which will flow from the terminal B2 to the emitter. This current is due to the minority carriers in the reverse biased diode. So this part represents the leakage current, you can see here. So this current is the leakage current. When the voltage is increased, VE is increased, there is a from 0 to some value, the leakage current will be there from the terminal B2 to the emitter. Now above a certain value, we are interested from here onwards. So above a certain value of VE, forward current, emitter current IE begins to flow. So this is the forward emitter current which begins to flow and which increases until the peak voltage VP and the current IP are reached at this point P. So at a particular point of VE, the forward emitter current starts to flow. Up to that time we will have a leakage current, and the forward emitter current will increase up to a particular voltage value represented by VP in this diagram, and it is represented by the point P. Now after the peak point P, when we try to increase the voltage VE, it is followed by a sudden increase in the emitter current with a corresponding decrease in the emitter voltage VE. That is, when we try to increase the VE further at this point P, what happens is that there is a sudden increase in the emitter current IE with a corresponding decrease in the voltage VE. So this region is called negative resistance portion of the curve, because with the increase in current the voltage decreases. So this portion is called negative resistance region. Therefore, we can say that the UJT has a negative resistance region which is stable enough to be used with a great deal of reliability in many areas like triggering the circuit, sawtooth generators, timing circuits, etc. So this region is of great importance, that is negative resistance region. With an increase in current, there is a decrease in voltage. Now, once it reaches a particular point represented by the valley point here, this negative portion ends at this point, and the current further increases with a constant or small increase in the voltage. So this point is called the valley point. That means the negative portion of the curve lasts until the valley point V is reached with valley point voltage VV and the valley point current IV. So the current is at this point, it is IV, valley point current, and the voltage is represented by VV, the valley point voltage VV. So this is the typical UJT characteristics, that is, when the applied emitter voltage VE is increased from 0 to a particular value, there will be a leakage current through the channel from the base B2 to the emitter. When it is reached a particular value, the forward current starts to flow. That happens when the voltage VP is equal to eta VBB plus VD. The current starts to flow through the circuit, or we can say that the forward current starts to flow. So this forward current IE increases with increase in VP, and it reaches a maximum value at the point P. When it reaches this point P, when we try to increase VE further, what happens is that there is a sudden increase in the emitter current with a decrease in the voltage VE, and that region, this thing will continue until it reaches a valley point, that is, the voltage is decrease in the voltage become stops, or it is ends at this point and valley point, and the region between the peak point and the valley point is called negative resistance region, because where the voltage decreases when current increases through the UJT. And after that valley point, we can have the usual thing that the current increases with a small increase in the voltages. So that is the characteristic of a UJT. Now if you consider this diagram, here you can see a typical family of VE versus IE characteristic at different voltages between the bases. It is clear from here that the peak point voltage falls, this is the peak point voltage which falls steadily with the VBB, and so does the valley voltage also, VV also falls. That means VP is equal to eta VBB plus VD, as as VBB falls, VP also falls, and that you can see from this diagram. And also the valley voltage is also falling with VBB. The difference in the voltage VP and VV, that is VP minus VV, is a measure of switching efficiency of UJT and can be seen to fall off as VBB decreases. That means this difference VV and VP, that is VP minus VV, also falls with VBB, and it actually represents the switching efficiency of UJT. Okay, that's all about the UJT characteristics. So that's all about the entire UJT discussion. So now we will discuss about the special type of amplifier which is called the operational amplifier or op amp, that we will discuss in the next videos. Thank you.